So the title is actually supposed to be the concatenation operation for uniform orient matroids and simplicial or simple polytopes, but I abbreviated it. And what is it? It's an operation for constructing examples of things, and it works for several different kinds of things. If I have a set X, which is linearly ordered by the indices, and I have a collection of subsets of X, if I have two things like that, W1 and W2 up there, then the concatenation is the collection of subsets on the same underlying set, where we take the union of a set C1 from the first from W1 and a set C2 from W2, and if the last element of C1 is the same as the first element of C2 in the linear ordering, then we can take their union, and that's an element of the concatenation. So so that's W1 concatenated with W2. And here's an example. Each of the three rows here represents either an uniform oriented matroid of rank 1, or a polytope of some dimension with two more vertices than its dimension. And in the first row, I have to tell you what the sets C are. In the first row, AB, the pair AB is in the set script C because I'll call those circuits, I guess. So AB is a circuit of the first oriented matroid, I guess, because there's a 1 and a negative 1 underneath them in the first row. So if they have 1 and negative 1, that's one of the circuits. And BD is a circuit in the second one for the same reason, and DE is a circuit in the third one for the same reason. And if I take the first two rows and concatenate them, ABD is a circuit. And then if I concatenate all three of them, or ABDE is a circuit. So there are two circuits that I mentioned there. We'll look at the other one later, maybe. And where did it come from? These are actually, in the oriented matroid setting, they're unions of oriented matroids. It's the union operation. Las Vernas showed that if you have two orientable matroids, then their union is also an orientable matroid. Weinberg asked me if there was a union operation, and I told him that if it didn't bother him that you had to put the elements in order, there was one. And so we constructed a union operation for oriented matroids on an ordered set. And Weinberg was interested in that sort of thing. He was an electrical engineer, at NYU, New York University, and he was interested in using Matroids and applying them to electric circuit construction. And this conference is called, I think it's called Matroids, Oriented Matroids and Applications. So we just finished the applications part of my talk. Now, for the Matroid part, some people claim that there's no relationship between Matroids and oriented Matroids, and sometimes it does seem like that. But these things are sort of, some of them anyway, are related to ladder path Matroids, which are all orientable, and you can get the orientation by looking at some stuff like related to this concatenation operation. Another place that's sort of interesting where things are related to the concatenation operation is in Jürgen Richter's work on finding oriented matroids with a small number of mutations, a small number of simplicial topes. Anyway, here are some things that people have looked at using concatenation or something like that. There's some contractibility results for concatenated oriented matroids. And so if you only looked at unions of oriented matroids, you might get the idea that all the realization spaces were always contractible. Of course, that's not true. Somebody figured out a nice way to see that it's not true, spectacularly. And Richter's construction, and is another one, and a third one is when Weinberg and I first wrote down what this particular union operation would be. I was looking for places to use it for something, and I discovered that the Klee walk-up counterexample to the unbounded Hirsch conjecture could be written down quite easily as a concatenation. We'll look at that in a couple of seconds, not in much detail, but we'll, see. Where did I go? There are some other things there. Let's look at the other circuit now. Let's see. AB is a circuit in the top one. B, C star. In the second row, B and C both have ones, and the asterisk means that in the oriented matroid, which have signed elements or elements in their negatives, B and C are both B and C both have ones there, so that's not a circuit, but B and C star represents the negative of C, I guess, would be a circuit. And so B and C star are circuits, C star and D star are circuits, and so A, B, C star, D star is a circuit of the concatenation. And from the concatenation, in exactly the same way, if I had alternating ones and negative ones on each row, then we would get alternating oriented matroids, or cyclic polytopes, combinatorial types of cyclic polytopes from that. So that's sort of the simplest possible case of concatenation, and we get the alternating oriented matroids. If I have a combinatorial pseudo-manifold, so that's a simplicial complex in which all the simplices have the same number of elements. So I could have one of dimension 2, which has triangles for its simplexes. And the property is that if I take a simplex and I look at any facet of it, there's exactly one simplex that has that same facet, exactly one other one that has the same facet. So in this picture, I can replace A by D. It's easier if we look at complements. So the property is that if I have, I'll call the complements of maximal simplexes, the facets, I'll call the complements circuits again. And if we have a point P that's not in a circuit, then there's a unique circuit that has P in it and is otherwise contained in C. And that's a combinatorial pseudomanifold. And the concatenation operation, if we order the set X, we can look at the concatenation operation, and it preserves combinatorial pseudomanifolds. That's very easy to see. In fact, I could probably do it here. So if I have two rows that represent, these are that's the underlying set in order. And if I have, what's a circuit of the concatenation? Well, I have a circuit here, and I have a circuit here, and they have the last element of this one is the first element of this one. And then if I have some element over here that I want to add to that, I have to take something out. There should be a circuit that has this new element and is otherwise contained in the original one, which is the union of those two. So if it's here, say, there'll be a, is this one? Then there'll be, this is a combinatorial pseudomanifold. If this is a combinatorial pseudomanifold, I can replace something in here by that. If the something is here, then we're done. The first element of this one is still the last element of that one. If it's this element, then we take this out, and now there's a new least element, which is bigger. It might be this one. And so I have to add this to this side, and once I do that, I have the two circuits I need whose union is the circuit of the concatenation. If I have, what's a uniform oriented matroid? One way to think of it is I have these n elements, and they're negatives, or the elements with the other sign, opposite sign. And in each, I have a bunch of circuits, and in each choice of, I take a choice of x1 and x1 star, x2 and x2 star, and so forth. In each subset like that, the circuits should be a pseudomanifold, a combinatorial pseudomanifold. That's, that would be a definition of uniform-oriented matroids with the other condition there in the middle about where the circuits are. Here are some properties that are preserved. First of all, if W1 and W2 are combinatorial pseudomanifolds, then so is their concatenation. And then it's the same sentence with combinatorial types of simplicial polytopes replacing something, and uniform-oriented matroids replacing something. And finally, if I have two realizable uniform-oriented matroids, or I could keep going here, if they're really uniform. The bottom one is I have two realizable uniform-oriented matroids, then concatenation is also realizable. So if I want examples of these things, I can start with small ones and build, or simple ones, and build up examples. I want to talk about two simple ways to do that, starting with, say, uniform-oriented matroids of rank 1. So if I take a bunch of rows that look like negative 1s and 1s, we've seen how we get the concatenation, we get oriented matroids of higher rank where the circuits have more elements by concatenating them. But also, so gamma is the class of oriented matroids that we get by concatenating uniform oriented matroids of rank 1 without changing the order. So for gamma, I have a matrix of negative 1s and 1s like the ones we saw before, and I can look at the concatenation. The order doesn't change. I mean, it's a fixed order, fixed linear ordering. But now let's look at this. So here the U's represent the ground set for one oriented matroid, and it's the concatenation of 2 of rank 1. So the rank is 2, and the circuits are, for example, U1, U2, U3 is a circuit because U1 and U2 in the first row have opposite sign, and U2 and U3 in the second row have opposite sign. And I think that the circuits in that one look like UI, UJ, UK, where I and K are congruent modulo 2, and the other one is not. So that's the U's, and now we can reorder them. And so in this bottom one, it's still, each row is still that same oriented matroid, and so U1, U2, U3, for example, in each row is a circuit. And so in the bottom row, in the bottom one, in the first row of the bottom one, the first 3 U's are U2, U5, and U6, and they form a circuit in the U matroid, oriented matroid. And the next, on the bottom row, underneath V3, V4, V5, we see U1, U4, U7. They form a circuit. So the union of those two is V1, V2, V3, V4, V5. That's a circuit. And so we get circuits that way. And we've changed the order. So this one's not in gamma. It's, so I can concatenate uniform ones of rank 1 and get bigger ones and reorder things and get others by concatenating those. So I get a much bigger class probably, which is phi. And what I mean by phi, I want to say that phi is the class I get by, that's closed under concatenation, where we get to reorder things, and it's closed under minors and duality. Now gamma is already closed under those operations. If I just look at the matrices and take the concatenations, gamma is closed under those operations. But for phi, it's more complicated. I have to add a bunch of more oriented matroids to make it get a closed set under those operations. So phi is much bigger. Now, these gamma has been looked at quite a bit because it's pretty easy to see, to find circuits and things in gamma and analyze what happens, I mean, relatively speaking. And so if I have a conjecture about uniform oriented matroids, say, then I might look at gamma and prove that the conjecture holds there and think of that as being evidence that it holds for all uniform-oriented matroids. But it seems like the things in gamma are pretty nice. So they have lots of things are true for them that we would like to be true. So it might be a little misleading sometimes to think that that means something. Phi is bigger, and I don't know much about phi, but I do know that it has this example in it, and this is the Klee walk-up example. So if I look at U1 up to U5, that's the complement of a facet of a polyhedron in 4 dimensions. It's the vertices of the complement. And U5 up to U9 is another one. And if I go from one to the other by pivots, it takes more than 4 pivots to do that. That's the point of the example as a counterexample to the unbounded Hirsch conjecture. And so that's something that you can't get from the gamma-oriented matroids. They all satisfy the Hirsch conjecture, I think. So it might be nice to look at these two, and I would like to know more about these classes themselves. So what is it that makes the things in gamma nice and so forth? So here's some questions. The first one is, of course, when I realized I could get the Klee walk-up example, I thought, well, I'll just concatenate some more and get a counterexample to the unbounded Hirsch conjecture, to the bounded Hirsch conjecture, which was called the Hirsch conjecture after that, I guess. And so I tried that, and it was much too complicated for me, but there's still this problem here. The second one is, can we characterize these classes of uniform-oriented matroids, say, by excluded minors? And the third one says, if I look at, it says something about mutation count matrices, whatever those are. It's like F vectors of polytopes, more or less analogous to that. And the question is, what can they be for the elements of these classes? That would be nice to know. And finally, there's a conjecture of Rencontres about if I have an arrangement of hyperplanes, then some of the regions might be bounded by all the hyperplanes. That's a full region or something. Complete region, is that what it is? And Jorge and Montijano look at this. I was wondering, I think you did it for gamma? Yeah. So they proved that Rencontres' conjecture holds for gamma. I think maybe if you were looking for a counterexample, a good place to look might be phi. But then it could be true and you wouldn't find one. That's it, I guess. I think. Let's see.
Okay, thank you very much.
Yeah.
Any questions?
So when you do the concatenation, the diameter of one and the other, so how does that relate? Is this bounded by some polynomial, or what is the relationship there?
I didn't understand.
So the question is, if you know the diameter of one and you know the diameter of the other, of the polytopes, and then you do the concatenation, what's the diameter then of the concatenation?
Oh, if you know the lambdas?
Yes.
It's just the
sum.
product, I guess.
The product, okay.
So, yeah, I think that's right.
Okay.
The product. Makes sense?
Any other question? Okay, so thanks again.